So now let's look at everything we did earlier and combine it all together. And remember we talked about Hertz contact is finite. It's a spring. Kinematic couplings give you exact location. And when you read in the text, you'll find that there are subtleties like friction, things that even that limits them. And then we said, well, we don't want, when you push down with the Hertz contact forces, to be so high that you dent and hurt the surface. So you got to be careful. And one of the ways to avoid that is by putting your V grooves, for example, on a spring. But all that should be in your brain now, going around saying, huh, ooh, we just said that Hertz contact was finite stiffness. Boing, 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 boing. And if I push too hard, ow, it hurts. But what if I can take that elasticity in the Hertz contact and make it such that as you're pushing, before it hurts, two flat surfaces engage? That is what the essence of a quasi-kinematic coupling is. A quasi-kinematic coupling was designed such that it can be parts that are cast, machined with a simple rotary tool to give you a V groove that's good enough. And then when you bring the two bodies together, you initially have a gap between the two elements. Here's the top element. And here is the bottom element, the quasi-V. And it's a quasi-V because if you cast the circle with these being reliefs, then come in with a tool that is shaped like a countersink, you're going to be left with these high regions. That's good enough close to a V. Now when you push, if the ball element can be an insert which is hard steel, the V groove or the quasi-V can be from a much softer material. You push down and you get a deformation, a Hertz contact deformation, until the two parts, the planar regions of the parts touch. And then all of a sudden the stiffness increases greatly, and the harder you push, the force now goes through the face-to-face joint as opposed to the Hertz contact area. You let go and boing, things spring open because there's always some, in metals anyway, some elastic recovery in a joint or in a break, in a contact. And now you're left with a gap that's a little smaller than originally you had, but it's still a gap. Such that now if I take the part off and put it back on, I've got a smaller gap between the two, but I still have a gap. And I have a conformal surface, so it's not a true V, it's a socket that engages the ball at 2 points. So as long as that particular part comes back to that particular base, and it has to be such that this ball will go to the particular V groove it was in before, which you can do if you create what's called a poka-yoke between the two parts to make sure it only aligns this way, it never aligns that way. You can get very good repeatability on the micron level with these quasi-kinematic couplings. And the nice thing is that you have a very simple casting of these reliefs, very simple form tool to make this simple groove. You put your parts together, tighten them, cause that initial Brinelling or that indentation when the Hertz stress is very, very high. Undo the bolt, it comes apart. You get a very, very robust coupling. So good, in fact, it actually was Professor Marty Culpepper's doctoral thesis some years ago, and he had initial application for engine blocks. to allow what's called the bed plate, which is where the bearing half for the crank is, to be mated to the heads, which is where it has the other half of the bearing for the crank. And he achieved cost reduction and far better alignment between the two than you got from ordinary dowel pins. Turns out we use this quite a lot, not in engines anymore, limited, but all sorts of mechanical devices where you want to have two parts very, very cheaply brought together, precisely kinematically aligned, tighten the bolts. Now they form a tight seal between the two of them, particularly for fluids, for example, fluid pump bodies. Very, very powerful tool. Now let's look at the condition where I want to bring parts together very, very precisely, and they're exactly where they were before I started. But you know, something else has changed. So now bringing the parts back together very, very precisely, remember precision is equivalent to repeatability. Accuracy would be bringing them to the exact known location with respect to some reference datum. What if something else in the machine changes? This was the case we did with for semiconductor test equipment for Teradyne Corporation. They made these test heads, and a test head is slipped over by a machine called manipulator. You can see here it's slipped over, boom. The technician aligns it by looking to make it a coarse alignment, and then connects it to, in this case, this is a prober. The prober is used for having the test head, having little electrical contacts that come down and touch the contact points on the wafer so they could do 100% inspection of the die on a silicon wafer. And then the wafer could be marked such that when it's cut up in individual die to be packaged, if there's a bad die, they don't have to package it. It allows them earlier on in the process to go back and correct, for example, problems that may exist in the actual manufacture of the semiconductor wafer. In the past, this coupling between the head and the base was often done with a much coarser type of coupling that would require the technician to fiddle with it a bit more, sometimes for as long as 10 or 15 minutes. And if you have to do that a couple times a day, you could be talking about significant fractions of an hour on multi-million-dollar pieces of equipment, which adds up to real money. So by making a kinematic coupling that can rapidly couple even this 1,000-pound test head, clunk, to within a few micrometers precision was excellent. But where the test boards were positioned between the test head and the part was good, but sometimes they found that the vertical position was okay, but the tilt was not exactly where they wanted it to be. Something was changing in the machine to which it was bolted to, and later on that was attributed to the weight of the test head and the way the parts in the system are mounted. They could get really good XY alignment, but this pitch and roll was a bit of a problem. How do we make the coupling come together very precisely in XY and even yaw, but be adjustable, not so much in vertical, but in the pitch and the roll? So this was Michael Chu's doctoral thesis, where what he designed was a system then where the ball effectively was on a post that could servo its position up and down. So there was an automatic latch that when you brought it into close position and got it mostly the way coupled, it would clamp it and then pull it down in, made it with the V-groove, and then the whole assembly could then move up and down just a little bit to enable that test head to adjust in its pitch and its roll. The accuracy he was able to achieve was very, very high, on the order of a few microns. And a very important thing was the repeatability of this coupling. See here on this data plot here, and forgive me, this is in inches, not in microns. this old method that was pretty much industry standard called a J-ring would be all over the place, up to 1/10 of an inch, which is why they had to fiddle with it quite a bit. The K-dock, or kinematic coupling, with this servo control, you really can't see the resolution in here, but it was within 3 to 5 microns typically. Very, very successful. Many, many thousands of these have been implemented. So as you see in summary, many different types of couplings. We're focusing on kinematic ones to start, many variations in kinematic. And then we're going to come back and talk about elastically averaged. Why? Well, because elastically averaged couplings are the opposite of kinematic couplings. And why do we want to think about something that's completely opposite when one thing works so great? Because exactly that. Always, always be thinking of, well, this is really great what I'm doing, but what if I do that? Can it be even better? Because if you don't, you know your competition will, and if you miss it and they get it, you're out of business. We're not going to let that happen.